Now we'll solve a few examples using this, and in order to do that we would just write this equation again over here. Delta K delta U equals work external minus FD. The delta K, we would in all cases consider some initial position and some final position. So for example, if we have something being pushed with a force and going up, and we want to find solve it between this initial and this final condition, so we'll say, okay, the delta K is the K final minus K initial, and that would be written as half m V final square minus half m V initial square. So that's how the delta K would be written. The delta U can be of two kinds. We have delta UG, which is the gravitational potential energy, and that will be well, this is the initial position, so it's going to be the UG final minus UG initial. We always take the final minus initial, and this would be MG Y final minus MG Y initial, or we can write it as MG Y final minus Y initial. So in this case, if this is our x-axis and this is our y-axis, this would be the Y initial and this would be Y final. So Y final minus Y initial would be this height, not this length, but the vertical change in the height. It goes from here to here. That will be Y final minus Y initial. That's one UG. The other is the U spring. So this is the change in potential energy of this spring, if there is a spring over here. And that will be U spring final minus U spring initial. And for the spring, it was half K X final would be the potential energy of the spring in this condition, and half K X initial square would be in the initial condition. So the spring stretches or changes its length from one to the other position. We'll use these. The work external would be F times whatever is the displacement, or the magnitude of F times the magnitude of the displacement times cosine of the theta between them, and the FD would be, well, F is going to be mu times the normal force times the displacement. The normal force would have to be found by using the sum of forces in the y direction, and it's not always simply mg. Now we solve using this equation, we solve a few examples. So let's suppose that we have an object that we hold at that point. This is the y-axis, x-axis, this is 0, 0. This is the y initial, that's the initial position of this object. So we know that value, and we are holding it here, so v at the initial position is 0. This is the initial position, and well, its mass is m, and then we release it. So as we release it, it starts falling down, the velocity keeps on increasing, and it crosses this point, which we take as y final, and then it keeps going. At this instant, the instant that it crosses it, the y is y final, and we want to find the v at this location, which we call v final. So let's the question is example 1, that if we drop that, v final is to be found given y initial, y final and well, maybe the mass of the object. Yes, we also need V initial. That's also given. In this case, we took it as 0, but it may not be 0. And then we write delta K plus delta U equals external work minus FD. The delta K will be half, oh, let's write it in detail first. So K final minus K initial plus U, in the K, the only potential energy here is gravitational, minus UG initial. There's no external work and there's no friction. Now, in most of the solved examples that are on Canvas in the practice problems, this has been written slightly differently. It's written as K final plus UG final minus K initial plus UG initial. So these two are written together and these two are written together, and it's written as K plus U final minus K plus U initial. That's how they are written, but it's the same thing. For these examples, we will use this approach, write them separately instead of combining them as done in those examples. So K final is going to be half m V final square. K initial is half m V initial square plus UG final is going to be mg Y final. So the gravitational potential energy is mgh, and here it's Y final, and mg Y initial for the initial value equals 0. Now we can simplify this. We can cancel out all the m's because it's present in all the terms, and we know the value of V initial could be taken here 0, so that this whole term would go to 0. If not 0, we know its value, and we know Y final and Y initial, so we know the G, the Y final, the Y initial, everything except VF square, and we can get VF square from here. This would go to the other side, and we would get 2G Y initial minus Y final, and if we take the square root, we get that answer. So we can solve this. Well, if we know the number, we can plug them in and get the answer. Now, as another example, we consider a level surface, and we have an object here which is pulled with a force at an angle theta, and let's mark this point as the initial position, and it's dragged along the floor up to here, and this is the final position, and the distance between these two positions just write as d. The mass is m, and there is friction, so the friction force will push backwards. The velocity at the initial position is vi, which may be 0, may not be 0, and the question is, what is vf? Now this problem can be solved by Newton's method. We get the fx and get the fx equals ma and get the acceleration, and from the acceleration, from the initial and final velocities, and from the distance we can get the final velocity. From the initial velocity and the distance we can get this, but we want to solve this by the energy method. So the question is, V final is what? We are given the force, the angle, the coefficient of friction, the mass of the object, the distance over which it has pulled over or dragged, and the initial velocity. So these are the things that are given, and the unknown is the V final. So we'll write delta K plus delta U equals the external work minus Fd. The delta K will be half m V final square minus half m V initial square. The delta U is there's no spring, so it's only the gravitational potential energy, and that's going to be mg y final minus y initial, which is the same because it's horizontal, so this is 0. The external work is going to be F d cos theta, so the F cos theta becomes its x component times d, so that becomes the external work, and the friction becomes mu n, that becomes the friction times d. And so we need to find the normal force, and we find that by taking the normal and the mg, and there's no other, well, there's a fy, fx. So the sum of forces in the y direction equals the normal plus fy minus mg is 0, so the normal is going to be mg minus fy, which is f sine theta. So knowing theta, f, m, and g, we get the normal force. Plug the normal force in here, and the d and the mu, all of these are known, and then so we have everything known except v final, and it can be solved.